Krishnendu and Jingting and Guan Yu for organizing this summer seminar. I feel like it's my duty to at least acknowledge all of them for their efforts on this last talk. And so the goal today is to well, let me quick give a reminder about last time. So last time we defined Motivic cohomology, and this should be interpreted as like over the um, Eilenberg-MacLane spectrum, or with respect to Eilenberg-MacLane spectrum. And we studied some basic aspects of it. And the one intuition, or one piece of one idea behind this is that under motivic cohomology represents, or in some sense generalizes um, uh, uh, higher Chow groups. So I can't remember if we actually said this fact or not at the very end of uh, uh, whatever day that was, Tuesday. But for wait, make sure I can write this down correctly.
I think briefly mentioned this. I think Professor Hoffman also helped.
Well, yeah, I mean, so if you, I mean, what I want to say is if you plug in a smooth scheme, um, then and you look at this motivic cohomology, it's graded in 2 degrees rather than 1. Then integral coefficients, then this recovers the Chow group, the higher Chow group, I should say, for x with respect to 2q minus p, I think. And I mean, I'll say that like these higher Chow groups may not have been encountered in like an intro to algebraic geometry course. And these are introduced by Bloch, and they're closely related with Borel-Moore homology. Anyway, it's not the purpose for today, but I just wanted to kind of recall some basic aspects of this idea. And so we should think of like, I mean, the basic idea in working with this category, this stable category, a motivic stable category, is this is where cohomology theories of motives live. And so a basic sort of construction or paradigm is, what we want to do is find interesting spectra in the stable homotopy category, and then use these to produce cohomology theories for our category of motives. And the exact method of doing this kind of depends a little bit on exactly what kind of spectra you look at. But this is a sort of vague idea. And so we'd already seen one example of this in terms of the Eilenberg-MacLane spectrum and what's called motivic cohomology. And so today, the goal is to do 2 others. The first is what's called algebraic K theory. And the second is algebraic cobordisms. And so I'm gonna try to do these. I mean, I think one area the notes is lacking is if is kind of like some motivation for the definitions. Like it's certain that you produce some spectra, and therefore there's these cohomology theories, but they lack some context in terms of where they come from. And so I think my for each of these the rough idea is I'm going to try to give some idea from topology, um, motivate where the spectra is coming from in terms of the stable homotopy category and topology, um, whatever that should mean, and then uh, use this to motivate how we might do this for the category and motives. Um, okay. Any questions on the plan? Not. Let's start with topological, or let's start with some recollections from topological K theory. This is like a very, very classical subject, so I'm gonna switch gears a bit, and we're gonna have X be a compact Hausdorff uh, topological space. I think it's perfectly fine also just to take it to be like a manifold or whatever nice things you want it to be. Then the complex topological K theory is a ring that we're going to define as follows. So the ring, which is going to be the Grothendieck group of the monoid of complex vector bundles, say E over X, and we're going to quotient out by vector bundle isomorphism. Okay, so I should give some more information. So I said this is, well, I think the first part that needs to be clear is, um, so if we look at complex vector bundles, I claim that this is a monoid. What do I mean by that? So complex. Let me write some notation. So let's call vec x these complex vector bundles modulo isomorphism. So I said that this was a monoid, so I need to specify what the binary operation is, and this is the Whitney sum. So the binary operation or the monoid structure, monoidal structure, is the Whitney sum, which is just a fancy word for direct sum. So I mean, if we have E and E prime vector bundles over X, then we can define E direct sum, E prime, and the fibers are just direct sums. So fibers, maybe just write like E direct sum, E prime, X. This is going to look like EX direct sum, E prime. Like nothing too interesting, or nothing that you probably haven't seen before. And in fact, we can so from a monoid, we can then take its Grothendieck group, and the Grothendieck group. What this means, so of a monoid, say M, what this means, and I'm gonna just use similar notation uh, for the binary operation. So what I mean is we want to look at two copies of M, and we want to quotient out by an equivalence relation that's by M1, M2 is equivalent to N1, N2, if there exists K such that if we do M1 and 2 K, this is equal to M2 and 1 K. And so, I mean, this is kind of an abstract definition, but the basic idea is that what we're doing is we're creating a like a free abelian, or we're creating a abelian group in sort of a universal way. And in this group, we have that 0 comma m is an inverse of m comma 0. So the problem is our monoid may not have inverses, and so we're kind of forcing those to exist. I think I said abelian groups, and maybe I should say commutative monoid or something like that. Anyway, so the resulting thing, what we get here,
This gives you the K0, right?
yeah, I'm not gonna, yeah, I mean, literally this is K0. I'm gonna pull a fast one and more or less only talk about K0 for just now, and later kind of sneakily introduce it. But I mean, it's still like I mean, it's still a cohomology theory, even at this level. Just not a, you know. And of course, like the higher, yeah, I mean, an annoying thing, and even like we're able to somehow overcome a lot of this by using yeah. Anyway, I'll say a little more later, but yeah, I mean, this is I'll probably just this K0. Okay. So anyway, the key takeaway is that we have like we actually have a monoid. We can take its growth in D group, and so this gives us an abelian group. And the last thing I want to say is that this is actually a ring. And how is it a ring? Well, just via tensor product of vector bundles. Okay. So we actually have a ring, and so here's some here's a fact. Um, is if we look at K as a map from I'm writing spaces for whatever nice spaces one might be working with, because anyway, why not? And going to rings. So as a functor, this is a generalized cohomology theory. Okay, and there's yeah, I mean, it's generalized cohomology theory. I didn't specify that what actually makes it functorial, but this is just pullback of vector bundles. So if you have x, y, e, then you can look at the pullback, and this gives it a functorality. And so a general question, and then you can ask is like, well, you can ask what spectra represents the cohomology theory, or so what spectra represents topological K theory? And so I want to build to an answer to this question, and the yeah. So let's first we'll first need a little bit about classifying spaces. So what I want to do is I want to take BUN as the space of n-dimensional vector spaces in infinite dimensional complex space. So this is uh, the classifying space for the unitary group. And we can define a spectrum via KUN. Well, I don't know. Hopefully this is correct. Krishnendra should be able to tell me if I'm writing something wrong, which is great. Even also running a seminar on K theory, so I think this is good. So I wanted to find a spectrum where in even degrees we're just taking. Oh, I should. Sorry, uh, let me say take BU to be the homotopy co-limit of these BUNs. Okay, now I can define a spectrum which in even degrees just looks like Z cross BU, and in odd degrees it just looks like U.
Yeah,
U.
it's true.
Oh,
It's correct. Yeah.
uh, do I want U?
Yeah, yeah. It's you. It's you. It has to be a. It has to be
Okay,
you.
okay. So I want U to be the homotopy co-limited.
Yeah, because your loop space of BU will give you U back. So
Yeah, yeah. Okay, great. Um, so in like whenever n is zero, you should think that like this is just what usually would classify complex vector bundles. So this makes sense. And when n is odd, we should expect there to be some like degenerate behavior. Like from well, not degenerate, but we should have like bot periodicity for topological K theory. So um the main I mean the theorem which this is where I'm just going to say this for arbitrary K theory, and if you plug in zero, you get for the degree zero part that I wrote earlier. So if we look at x plus is just the x with a point, and we you should say define a spectrum Ku, and well anyway, Ku actually represents this topological K theory. Um, okay.
yeah, so
And
this looks good because you are all doing it for complex version. The real versions look bit messy. It's instead of being two periodic, I think it's eight periodic. Like
yeah, yeah. I mean, so it's easy. It's still easy to define what it is at zero term because you can define the class. It's just instead of unitary, it's orthogonal. But the actual terms in the spectrum get a lot more annoying. Than, than
yeah, true. Yeah,
yeah.
yeah,
When we go to algebraic world, you actually see it gets easier, and part of this is just because of like instead of I mean these things are a little more rigid, and so specifying like a vector bundle on a yeah. Anyway, things are a little easier when you're working with like affine spaces, and anyway, we'll get there. Um, so I'll like one remark about like why should one like why is this so why does this theorem feel correct? I'm not going to prove it, so I'm just going to give like a uh some like vague explanation. And so well, like, what does it mean to be a classifying stack in this sense, or classifying space? Well, if we have X, um, so there's always a map to the classifying space. We have this sort of canonical map, and if we look over, um, if we take a vector bundle over X, then because this is a classifying space of complex vector bundles, I mean that's what this is. This classifies complex vector bundles, then we should automatically get that there's a vector bundle here along with a map from E to E prime that makes this into a pullback. And so what is happening is like if we have a vector bundle, we can produce a map here. And so there's still a lot, there's so much is missing in what I'm saying in terms of the actual homotopy theory. But one should imagine that this at least gives you a map from, well, if one does a bit of work, this would give you a map from here to um, KU, and at least maybe in degree zero. I mean, there's lots of things I'm not really saying, but so uh, I should also say, okay, so this gives you a map, for instance, like this, and then now one can start trying to upgrade this into the actual equivalence in the theorem. But yeah, this is just supposed to be some intuition. Any questions? Good. Okay. So like let's now do this for motives. So algebraic K theory, and I'm not well. One thing I'm not going to discuss is like what algebraic K theory looks like for not motives. I mean, this is like a really rich subject that has like a lot of interesting uh twists and turns in of itself, and a lot of like really hard work that went into getting it into like a really nice state. And so I'm doing it a bit of disservice by kind of skipping over this, but just for the sake of time, it's best to just think of this as a parallel with topological K theory than with like normal algebraic K theory for schemes. Um, and so here's first we need to deal with some preliminaries. So recall that we have this equivalence in the stable homotopy category of P1. I think this is something that Krishnendra showed last time, or maybe the time before last. I mean, sometime recently. Is that if we look at this mixed Tate sphere, then it ends up being equivalent as as P1 in the stable homotopy category. And so, what I mean, this should make it so you can more or less freely define things like P1 spectrums. And so we can go ahead and just write a quick definition. So a P1 spectrum, E is I mean, it's just the same thing that we have seen now probably a handful of times. En, along with maps, P1, En, 2En plus 1. And so, I mean, the P1 spectrums are a little more natural in terms of the types of cohomology theories we're going to encounter. It's really just a renormalization of the bispectrum that we've already encountered. It's just like notationally, I mean, it makes things a little cleaner for us. And I mean, part of it is that a lot of these theories that we'll discuss are like P1 stable. In some sense, like they have some periodicity with respect to suspension by the P1, so it just is a little easier to write. Did you have something to say, Krishnendu?
Yeah, the thing is that this S1 S mass S1T is same as saying it's the Tate sphere, right?
Mm-hmm.
At
No,
least in the
mixed Tate sphere or mixed. I think that's what they called it, right? I mean,
uh
the Tate sphere is the Tate. Sorry, Tate circle is this.
yeah,
Uh, Tate sphere
I'm
should
saying
be
Tate
this
sphere.
suspension with suspension.
No, that in the notes, I think they mention the Tate sphere as A1 minus A1 over A1 minus
Ah,
0,
yes.
and
This is the same as that. Yes,
same
yes,
as that. And
yes.
if you in the Guanu's talk in some past time when he was introducing Motivic spaces, Motivic spectra, they do take the Motivic spectra as a spectra over the Tate sphere itself, not considering the simplicial version and the Tate circle version like individually.
Mhm.
So I think this P1 spectrum is more connected to in that sense, like in the in the Tate sphere version of the Motivic spectrum. So
Sure. Yeah. I mean, this certainly is also equivalent to uh, what is it? A1. This is what you wanted me to write.
yeah, and I just wanted to point out that this P1 may look new, but I think we have encountered this beforehand as a Tate sphere, as a suspension with this T thing. So
Yeah.
that's what I wanted to mention.
Yeah.
Yeah.
No, it certainly is not anything new. And it's also like you can think of it literally as a scheme, and it's very useful to think of this in terms of its complex points, would just be a sphere. Okay. Um. So if we have uh so if we have a P1 spectrum, then what can we do? Well, we can define a generalized cohomology theory, and it's going to be bigraded, so in P and Q, and let's hope that I can actually get all my P's and Q's in order. So the key thing where like I mean the key difference of this between how we define like the Eilenberg-MacLane or the Motivic cohomology is that like we've replaced the Tate sphere with P1, or sorry, we replaced the Tate circle with P1, and likewise with the suspension. Um, and so, I mean, yeah, this just we can take this as an abstract definition, and we should. I mean, this is kind of like looping back to what I was saying at the very beginning, which is that like spectrum produce cohomology theories. Here's the type of spectrum, and it produces these cohomology theories. And so, I mean, in both topological K or both sorry, algebraic K theory and algebraic cobordism, they'll rise via this type of P1 construction. Okay, so
So this EP comma Q is your
it's oh you
go
mean
ahead, go
yeah.
ahead.
It
You're
is
writing that.
EP coming Q is the cohomology theory. I mean, so it's
Okay.
like this is a functor that takes you from um yeah. I mean, this is a functor from Motivic spaces, pointed Motivic spaces, or sorry, not pointed, but spaces to say I don't know
Abelian
abelian
group.
groups.
Yes, yes.
Yeah,
It lands in abelian groups. Yeah.
yeah. I mean, you can upgrade this to be just some spaces to like bigraded rings or something, but yeah. Anyway. Okay. So the goal now is to kind of come up with an algebraic version of this. I mean, we want to do is create an algebraic version of this KU spectrum from topological K theory, and so we can define uh, 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 well BGLN. This is going to be the uh, moduli space of n-dimensional uh, vector spaces in A infinity. So this is not a scheme, this is an in scheme, but that is perfectly fine because an in scheme is automatically going to be a uh, oh actually that may not be true. Oh well yeah, no, it should be fine. Yeah, because motivic spaces are um co-complete. Is that correct? I
I mean,
uh,
Motivic spaces are like contravariant functors into the simplicial sets, right?
Yeah.
So
So this is certainly, yeah. This is fine because every end scheme is a risky sheaf, and so it's automatically going to be in a Stavich, and we're fine. So anyway, this can be viewed as a motivic space, even though it's not like in the. I mean, it's a smooth end scheme, and that's fine. Um, and so what I want to do is replace um ah well I think uh okay, so anyway, this is fine. Um, and then we can create a sequence in Motivic spaces that's going to look like BGLN plus 1, BGLN n plus 2, and so on. So I mean, there's these canonical embeddings, just like in the normal Grassmannian case, which not well, and yeah, sorry, they're canonical embeddings, and they just come from sort of like freely extending these uh, uh, n-dimensional planes and n plus one-dimensional planes, and we can then take the colimit to get BGL, which again is just in our category of spaces. It's also pointed in that there's always like sort of canonical and dimension or well yeah it's always pointed because there's always a canonical zero-dimensional space, and we can just look at that as a point in this infinite union. Um, so we have a colimit, and then I mean the problem is that this may not be vibrant, so we can just using we haven't really talked too much about the model theory, but we can uh, then take uh, KGL to be a vibrant replacement of uh, uh, well, I want to add a copy of the integers, but um, so Z cross BGL. And so we should think of like BGL as classifying vector bundles in the same way that BU did for complex vector bundles. We just have a little more flexibility, or sorry, a little more um, niceties when working with algebraic geometry, and that like a single object does it, and you don't really, I mean, see these weird behaviors between like real or complex K theory. I mean, it kind of all works out fairly nicely. Um, but anyway, yeah, we can do this. And what is like what does Bott periodicity say? So in this case, what is Bott periodicity says that there exists an isomorphism um, from Z cross BG L to our loop zone of omega P1 for Z cross BGL. And the upshot, or I mean, the takeaway is that there's a map is beta from P1 uh, smashed with KGL to KGL. So it's kind of like, I mean, this is a lot stronger or a lot nicer than what we encountered with like complex uh, topological K theory, and that here we have no like the spectrum can be taken to be just KGL for each of the terms rather than
Exactly. So there is no it is basically one periodic, not two periodic.
yeah, exactly.
Okay,
Yeah, and
okay.
this is also why it's nice to use P1 here, just because it makes it as such, right? If you had picked a different
Yeah, 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 yeah.
normalizer, yeah. So we can, I mean, yeah, the can then define a P1 spectrum, and I'm going to denote this KGL just to make it look visually distinct from uh, before, but it's just an infinite sequence of these KGLs. And this formula from before tells us that we have a generalized um, homology theory um, KGL P comma Q, and I'm not going to write it out, but associated to any motive, we can do this. Um, and this is what we call algebraic K theory for motives. And yeah, so I want to say uh, one last important feature of this before we go on to cobordisms, which is if we have, I mean, we have a functor um, from the stable homotopy category of motives to the ordinary stable homotopy category for topological spaces that's given by taking the C points, right? So if we take the C points here, we produce a topological space. And what this functor does is, well, it is yeah, I mean, what I'll say what it does is it takes KGL and it takes it to KU from 4. So we actually recover the complex topological K theory spectrum. And so this is actually really an enhancement of topological K theory in this way, almost more so than algebraic K theory. I mean, there's certainly relationships between algebraic K theory as well. I just am yeah, yeah. Okay. Any questions?
Not a question, but just it feels very cool, looking at this Motivic
Mhm.
analogs of the topological version. So yeah.
Yeah, I mean, one thing I've noticed just from like trying to read on this stuff while preparing is that there's like a like the number of spectra you can define in the stable homotopy category for motives is kind of insane. Um, and I mean, I think one aspect that we haven't really talked about is like how can you use these? So of course, like you know, really cohomology theories are most of the time these are like really complicated to compute or anything with, but they can be sometimes useful for individual problems. So we haven't really had a chance to talk anything about that. But it's almost like it's very, very easy to come up with these spectrum, especially given that it has kind of this combination of the ones for this um, stable homotopy of like simplices as well as like different aspects of topology coming from like schemes. And so there's a lot that you can do. Yeah. Okay. So what I want to do now is talk about cobordism. Um, oh, sorry. There's one remark I should say. So I said that there is a relationship um, between this and algebraic K theory. I'm just going to like state what that result is because it is. I'm not going to go and define what algebraic K theory is, but it's kind of similar to this one that we had for um, the Chow uh, higher Chow groups and Motivic cohomology. And so this is this algebraic. This should be for like X in schemes. So this is for algebraic K theory, like uh, from Quillen. Okay, okay. Let's now get into some cobordisms. Um, so I want to explain like very briefly and roughly what like cobordism cohomology is from the perspective of topology, with mainly the lens of like how can we go and find the this or what is the spectrum. I know very little about like like smooth, complex cobordisms theory and whatnot, outside of like, what little I've seen in my topology classes. So I'm certainly not the most qualified to be explaining this, but we'll hope for the best. So here I want to work with complex manifolds, and I want to explain what it means for two morphisms to be um, cobordant. So if we have two maps into X, these should be proper and complex oriented, then they're said to be cobordant if there exists a complex oriented map B from W into X cross R. Well, such that like um, when you look at B and you restrict to um, X cross 0, then this should just be F. And when you do the same for X cross 1, then this should be G. So, I mean, this is a nice technical definition. Here's the actual picture that one might want to keep in mind, or what I think is the picture. So we have some space, and I mean, this is maybe not quite what it looks like, maybe something like this. Um, and so this is our space W, and then sitting inside of it, we have like these copies of Z and Z prime, and then we have this map B, which is going into this tube. This is our X cross R tube, and at 0, yeah, so you have 0 and 1. Then when we look at just like this piece mapping in, well, it should map as I'm drawing it, and then this is F and this is G. So we have some parameterization of like the manifolds that takes you from F to G through a smooth manifold itself. This is like, I mean, if you like want to say what like it means for two manifolds to be cobordant, it means like you have another manifold that or I guess it's bordant rather than cobordant. But if you want two manifolds to be bordant, then it's saying that there is another manifold whose boundary are those two manifolds. So this is kind of like a map definition rather than a manifold definition. Okay. So what can we use with this? Well, I'm not going to prove this, but the uh, cobordance defines an equivalence relation on well, these nice maps, that proper complex oriented maps of uh, relative dimension Q, uh, and so we can take the quotient by this, and this is what we mean by topological cobordism. So we can define mu q of x to be this set of maps modulo cobordism. And the fact is this actually defines this is a generalized cohomology theory.
Yeah, this is your classical mu spectra if you are talking about the topological version of it. I'm expecting
Yeah,
there is a okay.
yeah. I mean, this is so far. This is very. I mean, this is yeah. The I mean, that's why I wrote mu and for the cohomology theory. But yeah, I mean, so this yeah. The I mean, the follow up that we should have now as I don't know aspiring homotopy theorists or whatever is uh what spectra does this represent or what spectra represents this cohomology theory. So, yeah. So I'm going to give the answer, and if maybe Krishnendu can be able to explain why this is the correct answer. So what one does is you can define this space mun, and this is the Thom space. I think this is the notation we used before for this. And so it's a Thom space of the or of the vector bundle EU sitting over BUN. So EU is the total space. I mean, this has a tautological vector bundle, and that's this EU. This is the total space of the classifying space, and we can then look at its Thom space. Let me write some words here. So this is the total space. You can also think of this as like, we have that this is like BUN is the same as this Grassmannian, and so it's a Grassmannian, so it comes with the tautological vector bundle. So EUN is the tautological vector bundle. So it's a rank n vector bundle. Okay, and we have maps. I should explain what the I mean this I'm claiming that this will give us spectra, so I should explain what the um, maps are. So we have UN sitting inside a UN plus one, and this will induce a map from S2, and we'll give some more care in defining this in the algebraic side. To MUN plus one. And so this defines a spectrum, which I'm just going to note mu, and then the theorem is that mu represents a topological cobordism. Yeah, I like I really don't come from a place of topology or geometry, so I really don't have any intuition for like why is this the correct spectrum. I know there's general like ways of constructing these from cohomology theories, but if maybe someone has a better answer. Um,
This
Yeah, the
is
better
not the
answer is that this is a Fields medal for Renee Thom.
uh, yeah,
That's
I
the
mean,
answer. Okay.
Sure. Okay. Well, thank you for that. If we're happy with that, then we can move on to the algebraic version. Okay. So for algebraic cobordisms, um, I mean, there's a mild annoyance in like just dealing with like uh working between like complex manifolds and topological spaces, and like how do you actually even define what the total space is. And so I'm going to give a slightly different like perspective on this than before, but it's all more or less equivalent. I'm just like not going to really get into like what the total space should mean in the most literal sense. So what what do we want to do? Well, I want to define, well, but as I mentioned before, there's these Grassmannians come equipped with these tautological uh, vector bundles. So here I'm just taking n and m to be um, some integers, some positive integers. So this is the tautological um, rank n vector bundle. And what you're doing is just over every point on the Grassmannian, there literally is an n-dimensional space, and you're just taking that to be the fiber. And so what you can do then is this process is actually like um, compatible with respect to the canonical inclusions. So if we look at uh, n comma m sitting over grn m, and this is sitting inside grn n plus m, then of course, well, we have n m plus 1 sitting over here, but this is compatible, and we can construct a unique map here that makes this commute. And so by taking colimits, we get a uh, universal vector bundle, rank n vector bundle. And this is this is the colimit over all the n's. Sorry, I'm confused with this. Sorry, colimit over all the n's of these gamma n m's, and this is sitting over this infinite Grassmannian that we wrote before, and this is uh, BGLN. Okay. So what do I want to do with this? So here's an observation. If we consider the product A1 cross gamma n into our BGLN, so this is a product of vector bundles where I'm just looking at A1 as a trivial vector bundle, and then gamma n as being like the usual one. So this is the product of bundles. And what does it mean to be like? Well, anyway, what the observation is that this map or this vector bundle is classified by the inclusion BGLN into BGLN plus 1. So what does this actually, I mean, let's unpack this a little bit. So we have A1 over gamma n, and this maps to BGLN, and then this in turn maps into, sorry, let me write this correctly. This maps into gamma n, and this maps into BGLN. Oh wait, I'm confusing myself. Maybe let's ignore this part for now. I mean, what I want to write is that we have a pullback square. Okay. Sorry. So here, let me change this. So there
I
exists.
think your BGLN should be BGLN to BGL
yeah.
plus 1 should be on the bottom. I think that was the confusion.
This
Yeah,
is what
that
I
also
want.
works good.
So there exists a map A1 gamma n to gamma n plus 1 classified by the inclusion. This is, I think, what I want to say. Okay. The takeaway is that we actually, I mean, the key component here is that we have this map that we want. And why do we want it? Well, because we want to take we want to go, well, one observation from like topology, let me just kind of put this in the corner here, is that if we take the Tom space of A1, we'll get like a two sphere. So the idea is if we do this in algebraic geometry, then we get this P1, and this will give us our structure maps for the spectrum. So let's apply TH to this, and now we have to use some facts that Krishan either proved or we didn't prove. So of course this is sort of like monoidal, so it takes these smooth in schemes, and it produces smash product. And so we have these maps, and if we recall, this Thomas space of A1 in this world, it's A1. It's this Tate sphere. Okay. And from before, like we can identify this with like P1. Okay, so we get we get maps from P1 gamma n plus 1, and so we should imagine this is like being very analogous to what we did for topological K cobordisms. We already saw before that. I mean, these gamma n's, these are like the universal bundles over BGLN, and we already saw before that when we did topological K theory and algebraic K theory, that BGLN is kind of like the algebraic replacement for BUN, and then this gamma n is this replacement for EUN for the total space. And so this this produces a spectrum that we're going to denote by MU, and its terms are these, so gamma 0, column space for gamma 1, space for gamma 2, and so on. And oh, sorry, this is my notation's bad here. I want this to be MGL because we are working algebraically. And so this, as using the same model as before, this defines an algebraic cobordism cohomology, or this defines a generalized cohomology theory that we're calling algebraic cobordism. And I'm again not going to go into how that's actually defined. I mean, it's using that same model as before, but it's again bigraded, and we can associate to any Motivic space this. And just as before with topological K theory and algebraic K theory, we have a relationship that we get by looking at the C points functor. So when we look at the C points, taking us from our spaces to manifolds. So this would be on I guess the smooth schemes over say C, the manifolds. Then what does this do? Well, it takes it takes the spectra to the topological cobordism spectra that we defined earlier. And I think it should also be the case that there's some relationship with classical algebraic cobordism theory, although I don't know what that should look like. But yeah, I mean, I think that's more or less all I wanted to say. Just to kind of like summarize a little bit. We constructed these categories of motivic spaces, and we wanted to start performing homotopy theory on them, like one does in an intro to topology course. And so we started that by defining a version of like singular cohomology, which is this using the Eilenberg-MacLane spectrum, and the corresponding algebraic counterpart to that in the world of schemes was this Chow rings. And so now we've done this as well for topological K theory, which was this algebraic K theory, and topological cobordism theory, which became this algebraic cobordism theory. And the general model for all this is just cooking up different spectrum. And so I haven't really said anything about applications or any of that. So maybe that can be a topic for the fall semester. But yeah, thank you.
So let's give a vote of thanks to Bolton for this wonderful talk and wrapping it up. All right, let's stop the recording.